So today I want to talk about Brownian motion and random walk. So let's give a overview of Brownian motion. So the Brownian motion is a simple continuous stochastic process, and it has many applications in either physics or like economies or mathematical finance or other biology or something. There is many practical applications. Uh, so here is a pictures of a small particles, which is basically a physical behavior of the particle, and you can have a direct impression about the Brownian motion. Okay, so I want to briefly talk about the history of Brownian motion. The Brownian motion got its name from the botanist Robert Brown, who is a English botanist. And when he do his experiment, and he observed the pollen reaction with like water molecules uh, under a microscope. Here is a picture of Brown, and here is a picture of the specific detailed like some reactions. The blue one is a water molecule, and the red one is a pollen. Mm. Okay, so in mathematically, the Brownian motion described by the Wiener process. This is a continuous time stochastic process, and with four properties. The first is W0 is equal to 0. So this is means when the t is equal to 0, we normally notice that as the Wt. So when t is equal to 0, the W is equal to 0. And the second property is that when the probability P is equal to 1, the function Wt is continuous in T for every T. So the third properties is very important. So this is it describes that the process Wt for every T is greater than 0. When T is not greater than 0, it's meaningless. So when every T is greater than 0, it has a stationary independent increments. This means, for example, the W1 and W2, they are independent with each other. They do not like get effect or they do not affect each other's. Okay, so for the first one, uh, the increments of the Wt plus s minus Ws, which is during the period of t, has a normal distribution in 0t. Okay, so what is the random walk? How do we connect the Brownian motion with random walk? As we know, the random walk is known as a discrete time, a stochastic or a random process, which describes a path of a number like many random steps under a mathematical space. It can be ZD, or it also can be like RD or something else. In there, I only use, in this presentation, I will just use a ZD, which D is a dimension. Okay, so for the Brownian motion and random walk, intuitively, we consider the Brownian motion as a limiting case of some random walk as the time to 0 goes to 0. This is because we want to define make the Brownian motion, which is a continuous process to like to be more feasible with a discrete motion, with a discrete process. So here, as you can see, there is two pictures of the random walk and Brownian motion. So during the same time period, which is both 10, and you can see like at first glance, there maybe the tendency is very similar, but when you look at it in much more detail, you can see like there is more detailed information in the Brownian motion, since it is a continuous process, which means every seconds, every small partial will be considered and will be graphed. But in this random work, it just graph a basic things. So meanwhile, there are many like realistic examples or practical examples with Brownian motions as random work, and the paces for random work displays different properties. Uh, with d is equal to 1 to 2 to 3, and for high dimension, but we do not talk about high dimension today. And I will focus on dimension 1 and dimension 2. So for the one dimension work, consider a random work. So on a line, it has we define xp1, which is the positive one, and xp2 is negative one. You can just consider p1 as the possibility of moving ahead, and p2 is the possibility of moving backward. So the possibility, since it's random, so the possibility is equal. So we have the expectation value is equal to 0. Expected value of x is equal to 0. And the variance of x is equal to, using the formula, and we can get is equal to 1. So our goal is to describe the discrete random work to continuous Brownian motion. So we just define a formula as y with respect to like the I. By the computer graphing, we can get some pictures of discrete random work. As you can see, these are just separate points and without any connections. So as you can see, the I we define as 8. So there are like 8 points. And you can also define as many as you want. This can just to make the graph more detailed. So we can just simply connect like this paragraph to this graph to a together with all the points, and you can get a continuous estimation of the one-dimensional Brownian motion. So here we define a new formula with a y bar, and the t means, as I just said, is about, you can just think of it, divide t into n steps. So as many parts as we divided, we can get a more precise estimation of Brownian motion. So as there, when n is equal to 5, you can just get some straight line and it will not show many details. However, when n is equal to 100, you see the trend is basically they are the same or like the similar, but for this period, as you see, this graph when n is equal to 100 shows much more details, and also like you can only see it pass the origin for one time, but this pass origin for many times. So we can make an assumption that you may find the path of one-dimensional random work goes through the original points for many times. And this is because one dimension and two dimension, we have the property of recurrent. A famous example is the drink man will eventually find his way home. Either he walk along a line, or he works on the plane for two dimension. Okay, so as we already talked about, as n is equal to infinity, the oscillation with t can touch the origin for infinite times. Therefore, the one dimension and two dimension random work as Brownian motion. So like the p is equal to 0, p is equal to 1 as the random sequence is equal to 0. This is just a formula, mathematical expressions. So as you see these two paragraphs, this is a one dimension discretized Brownian motion, and this is the second discretized Brownian motion, Brownian path. They all just touch for the origin or come back for many times, and we just do not set it as infinity. As you set infinity, you can see a much more dense passes of it. So for the three dimensional random walk, there exists a very complicated formula for the triple, like the use the triple integral, but we just talk about one dimension and two dimensions specifically. And for the second dimension, you can see, consider a drink board. It cannot coming back to the origin because it's actually less than the possibility one. So you cannot expect it will always come back to home. Okay, thank you for reading and listening my presentation. Thank you.